attached to a blade, which is placed in the skimmer. The other end of the hose is attached to the vacuum head, and the head itself is manipulated by the telescopic hole. So you can see the skimmer here, the hose is attached to the head, and then the telescopic hole. The focus of our project is solely on the vacuum head.
So current products on the market, as shown here, this is actually the #1 commercially sold vacuum head. So based on its overall performance, they are very bulky, and if you can see on the bottom, they do have bristles that are already built into the vacuum head itself. So once it breaks, you have to buy an entirely new vacuum head. So that's overall our kind of approach to kind of fixing that. So we have the overall hose input that goes into it, as well as the telescopic hole hookup, which would be similar to our product. And like I said, they're very large and they sit flat on the surface of the hole.
So before we get into the goal of our project, we would like to thank Jim Lennox. He presented us this problem statement of optimizing a pool vacuum head attachment. So moving on to our goal, the goal of it is to improve the existing pool head vacuum attachments. We want to increase the suction rate at the head, along with improving the overall cleaning ability of the vacuum head. We would also like to improve the maneuverability of the head in the pool and also reduce the cost while improving the longevity of the product. So now for our mechanical requirements, we are going to 3D print the vacuum head base and the interchangeable cleaning attachment. The head base will be made out of PLA filament, which is not corrosive in water, and we will be using TPU, which is thermoplastic polyurethane, for the cleaning attachment because it has more of a rubber-like consistency. Next, we will be the telescopic handle attachment has to be the universal diameter of 1.25 inches, and it also must accommodate for the universally used wishbone clip to attach the telescopic pole to the handle attachment. That has to be made out of stainless steel along with the screws used to attach the two pieces, so it does not corrode in either a saltwater environment or a chlorine environment. The pool hose vacuum also has to be compatible with the universal diameters of 1.25 inches and 1.5 inches, so we don't need to change any of that. The vacuum head and also the interchangeable attachment, which will be a squeegee, will have to have implemented magnets that will be printed within the product so they're not exposed to water and therefore reduce the risk of corrosion.
So the overall specifications of our product, so it has to overall accommodate for a suction rate of 8.2 gallons per minute to 11 gallons per minute, which is relatively standard for commercial pool vacuum systems. The design must accommodate for all universal pool vacuum hookups, so the telescopic pole hookup as well as a hose hookup. And the design must encompass geometry that will make it be able to maneuver in both rounded pools and pools with corners in it. An interchangeable cleaning attachment itself, the squeegee, will be designed to be integrated into the vacuum head itself. With the interchangeable cleaning attachment, it will have a level of buoyancy, so if it does detach from the vacuum head, it will float to the surface for easy pickup. And the overall geometry and shape of the vacuum head will have to be built so it doesn't make direct contact to the pool floor or any vinyl that is put on the pool surface. And with that geometry, you must overall encompass the means to restrict or mitigate any possibilities of debris clogging the whole system, such as big debris such as leaves.
So our preliminary design is much different than the commercial vacuum heads. Part of what makes it unique is the funnel shape from the contact surface to the opening of are damaged over time or just start to wear down, you have to replace the entire vacuum head, which is approximately like a $30 replacement. For our design, our cleaning attachments will be replaceable, and that will be the only thing you have to replace instead of the vacuum head and the telescopic pole attachment there. Additionally, our design will incorporate a stiff handle attachment as opposed to the pin joint attachment found in commercial vacuum heads. This will eliminate the need for adding weight to the vacuum head, which is required to keep the head in contact with the pool floor. In our design, it can simply be manipulated by the telescopic pole, overall making our design a lighter weight alternative. Finally, we will have magnets implemented into our design. This will make it possible for the interchangeable cleaning heads and making our product cheaper in the end. As we previously mentioned, magnets will be installed during the 3D printing process to eliminate the possibility of water exposure and thus corrosion.
So the overall theory that went into our overall design parameters, we couldn't really find any specifications from the commercial market or anything like that, so we had to mostly come up with our own theory as far or kind of like our own legitimization of the theory. So strictly based on fluid dynamics, more or less, the initial kind of first step of our group was to overall legitimize the overall proof of concept provided to us by Jim Lennox, and that was overall by finding the coefficient of loss, or the K value, and looking at the different designs of both the prototype provided by Jim Lennox and the commercial vacuum heads on the market. Most of the commercial vacuum heads have some contraction, and the one provided with us, that were provided to us did have that sun contraction of 90 degrees, whereas Jim Lennox's proof of concept had a chamfered angle into it. So that does prove to be a little bit more efficient, and with more calculations we did come to the conclusion that 45 angle chamfer is the overall best way to optimize the design. From there, we calculated the overall head loss that would be conducted by each of, compared to the prototype by Jim Lennox and the commercial vacuum head, as well as coming up the area of suction, so the overall diameter outside of the overall entrance port, and this overall suction distance, so how the vertical distance from the vacuum entrance port to the pool vacuum floor, force of suction, and overall suction. So with these parameters and everything like that, to overall conclude that the prototype given by Jim Lennox is more efficient, we did set up an experiment. So to overall kind of simulate how a pool vacuum system actually works, we start with the pool vacuum hose attached to pool vacuum head attached to the intake hose, which was fed by a pump, and it would again outtake back into the water. So that is overall kind of process on how pool vacuum works in general. So figured that was the best way to kind of our best environment to test that in. Likewise, we set up a manometer, which all we need to do is tap into the side of the vacuum head squeegee attachment. So that was a 7.5-inch rubber strip with a 2.25-inch gap in general. And we did different iterations with 4 rubber strips and 2 rubber strips with different size gaps. So we did conclude that the 7.5-inch rubber strip with only one did prove to be more optimal for our design. So overall design considerations that we concluded from the experimental testing as well as our theory was overall circular geometry of the vacuum head. We compared geometry sizes as well, overall area and the circular cross-sectional area provided the best overall efficiency of suction. The size of the entrance port diameter was also a key factor. So the larger the port diameter, the higher the chance of loss of overall pressure from the overall system. Likewise, we included the chamfered angle of 45 degrees to implement more efficiency within the system. Implementing a fixed telescopic pole compared to those of the adjustable telescopic poles seen on the commercial market, and a lending attachment utilizing magnets.
So this is our preliminary assembly. It's a 3-part assembly with the telescopic pole attachment, the vacuum head, and then the replaceable cleaning tool that you can see on the bottom there. There is a wishbone clip inside the telescopic pole. You can see it over here on both sides there. That's how the telescopic pole is attached to the vacuum head in the industry. And then the telescopic pole attachment is attached to the vacuum head using stainless steels to prevent corrosion. Here's another view, a top view where you can get a better idea of what the wishbone clip looks like in the assembly. This is our pool vacuum head. You can see the angle there that we used, and then the arrangement of magnets in here, which are used to attach it to the cleaning tool.
This is the telescopic pole attachment. It will be made from stainless steel. It will be attached to the radius of the pool head base and attached with the 2 screws shown right there.
And here is the tool attachment. It has the same arrangement of magnets around the circumference of it. And then as we found from experimental testing, the circumference of the cleaning blade only spans 2/3 of the bottom of the tool, and then 1/3 is an open gap so that the debris can be funneled into the vacuum pumps. Here's another view of the replaceable cleaning tool.
So moving on to our ethics, we follow the basic NSPE code section 1.1 saying we won't endanger people, and also section 2.1a saying we don't want to endanger property or damage anything with our research and or design of our products.
So this is our work breakdown structure. It was separated into mechanical testing and management. Under mechanical, we have the vacuum head, the telescopic pole attachment, and the replaceable cleaning tool. Under testing, we use the manometer to test the vacuum pressure in both the commercial vacuum head and the proof of concept provided by Jim Lennox. And we use the pump to test flow rates in both of those.
This is our work schedule. So far we are up to date on everything.
Here's our Wilkes budget totaling about $80 compared to a realistic budget which is about $52,000. Our plan moving forward is to 3D print our preliminary design and test that design along with other prototypes, and we also want to set up the experiment that we've been doing experimentally in a computer software called Fluid to find computer simulations. Finally, we would like to thank Jim Lennox for this idea. We would like to thank Dr. Bednarz, Dr. Nile, our advisor, Dr. Whitman for help with the lab, and Mitchell Adams.
These are references. Questions?
I didn't see any analysis of the magnets and force that's with which it attaches the tool and how much force you need to detach it? And did you do any analysis on that?
So we haven't had the opportunity to perform that analysis. It was taken into consideration during the design, so there will be a very small layer between the 3D print and the magnets to hopefully optimize the amount of force provided by the magnets. But additional testing will need to be done to verify that, which we will be doing next semester.
So basically, there wasn't any analytical support for how much force you needed to hold it on.
No, we haven't, we did not order any magnets yet to do any testing as such to find out the force of the magnet. That is something we will take into consideration starting next
Okay,
semester.
thank you.
So, first thing, like everyone was talking about, the magnet, do you want to make the ejection or just permanent?
Perfect.
You do permanent, we have an issue here because that part needs to be strong. If you make it too strong, it's hard to take it off.
Yes.
If it's not strong enough, you have trouble as well. So, permanent, we have some issues. So, I mean, that's why you just couldn't take it off. It's
Yeah.
permanent.
Yeah, we anticipate that, and part of what we use $80 over budget is we'll have the opportunity to try different magnets with different strengths and just change our design as we need to account for that.
Okay. So the second is, I'm a big fan of experiment. So I was at the beginning, let me give you my thought process. Like at the beginning, I saw the design like two sensors and I saw the experiment. I was very happy to see that. I wish I could have seen a video of how you guys did that because it's actually a lot like you took a reverse approach. Then at the end, I was thinking you should do some simulation, but I thought that's too hard. And you mentioned you used Fluent. Just encouraging you, but American Tech can help you with that. That's not something as straightforward as you would like. Okay? Just encouraging you about that.
We are aware of that.
It's not a very small effort. Maybe that's why you took an experimental way first. I mean, that was a bit more friendly to you, at least. Okay. So finally, my comment is that when you were doing the testing, like, did you add any like debris in your water? Because that's the reality, right? If you didn't, then that's going to affect your results a lot, like in 2003.
So we just use plain tap water right now because, like Matthew mentioned, there was no characteristic values on the internet anywhere for the suction rate or any kind of value we needed. So we were just using that experiment setup to characterize values to be able to prove that proof of concept we were given is more efficient. And then, so now as we start printing our preliminary designs, we will be able to test them in, we're going to try salt water and also with chlorine treated water and then eventually add debris to mimic.
Yeah, because the thing about this, I mean, this slides, that side, I think about debris is a very important part of that's a very necessary part of this environment. And if you always just simulate the ideal situation, you're not addressing your problem. So again, I know that's going to mess you up, but I don't think that's something you would like to delay further. You understand what I'm saying? So, for example, add some leaves there just to see, get a general sense. I'm not saying make it too big, but at least much better than just using water, and otherwise you're not addressing the issues.
All right, thank you.
Pardon? The results.
Yeah,
Oh, you want the graph?
Let's take a picture of the experiment. Push up, so that manometer, where is it connected?
so it is connected to, you can kind of see it there. There's a little nozzle with the tube connects into. So it's like right at where the water system.
Okay. And the other end of it is that straight.
Yes.
That's the suction pressure that you can have.
Yes.
That is in this part. Okay. So you want to have the highest suction pressure, right? To if you want to continue on structural commands, just try also with multiple commands. Don't listen to you. Create them into a workload.
So how confident do you feel about this data? I mean, if they are good, you are really onto something. But how confident you are about this data? To me, it sounds a little bit too good to be true. I don't have time to dig into it, so I just want to force you. So I mean, if this is good, this is indeed correct data, then you are really onto something. You're in good shape. But just, I don't want to find you guys on the post.
I mean, we had similar setup for each experiment for both commercial and the proof of concept games with Linux. So we are fairly confident in this data. So we did adjust the overall flow rate from the each iteration of the data collected. And we did it fairly similar. Obviously, we did it a little bit more robustly. So it was just a lever. We adjusted it without an actual.
And this you did side-to-side comparison, right? So you see like your system has much more suction pressure than the commercial system. And that's kind of 100%